We have some time for questions, so feel free. I do have a microphone.
Can you explain why the Dreamliner battery is getting heated up?
Sure. I was actually talking about that a little bit earlier.
Can you repeat the question?
The question is, what's happening with the Dreamliner battery and why is it a problem? Batteries, the Dreamliner is a lithium-ion battery, uses lithium-ion batteries rather. And the challenge is charging and discharging the battery and doing that in a reliable fashion. The problem you run into is, one, if you have a manufacturing defect, i.e. the separator that separates the anode from the cathode, you can have an internal short. Let me back up a second for those people who may not have a technical background. Batteries work because you have two chemicals inside that want to react with each other. They want to react bad enough that one of them will release an electron and go over to react with the other one and grab the electron on the other side. So the electron has to go through an external circuit. And to recharge it, you pull the electron out by applying a voltage that causes the reactant to go back to the other side and plate out over there. In lithium-ion batteries, you have carbon on this side, and the lithium is supposed to go into the carbon and be stable inside the carbon, so it doesn't, it's not there as a metal that could create a problem. If you have a defect in the battery, i.e. a hole in the separator that keeps those two chemicals apart, if they touch each other, they can actually discharge through that hole and generate a lot of heat. A similar mechanism would be when you're charging the battery, if the lithium metal doesn't go into the carbon the way it's supposed to, if it plates on the top, you can start getting lithium metal plated, and that metal can actually plate in a dendritic form and go across the separator and create an internal short. Once you get an internal short, now the energy that you stored in the battery gets dissipated as heat. The battery temperature starts to rise. A couple things go wrong then. The electrolyte that's used in the battery is more like an alcohol. It can evaporate, it's volatile, it will burn. So when you start getting hot, you run the risk of a fire. Now what happens in a battery typically, as it starts to heat up, the electrolyte will actually start boiling inside the can, or the pressure goes up, and eventually it will rupture the can. Everything is hot at that point, and you can actually have those electrolyte vapors coming out and burning as they come out, and that's where the flame starts. Once that happens, then the lithium in the anode and the cathode start getting into the mix, and you can have a very violent decomposition. Does that answer your question? Thank you.
What would be the expected lifetime on your engine? So it has no parts.
It should last longer. It really should. There are other things, the basic mechanical problems that have to be addressed. One end is hot, other end is cold. And as you start and stop the engine, it's going to heat up and cool. So you're going through temperature cycles. That, of course, causes things to expand and contract. So you get these mechanical stresses. So all of those practical problems have to be addressed. Thermal stress is a major issue. The membrane needs to be reliable. One of the things that you don't want to have happen, since the low temperature membrane electrode assembly is driving hydrogen to high pressure, if you have a defect or hole in your membrane, the hydrogen can just come back through, and that's a loss of efficiency. So you're pumping one way and it's just leaking back, and so you'll see a degradation in performance. So there are practical engineering issues to be addressed in terms of how one would be able to deploy it in a reliable fashion. Go ahead.
I had a question on the lithium air cell. What do you see as competing technologies for driving, I guess, higher wattage from lithium ion?
Lithium air is, I think, generally seen by the battery community as the ultimate battery technology. What's interesting about that is that we started on lithium air battery technology doing our research back in 2004, a long time ago. Around 2010 timeframe, IBM made this announcement that they were going to start studying lithium air batteries, and all of a sudden the whole battery industry is excited about it. But we've got a good bit of intellectual property because we started on it before a lot of people realized what its full potential is. So in terms of the battery space, a lot of people see that as the ultimate battery. There are other batteries that people are working on. The solid-state battery is one of them. Generally, lithium air is seen as the ultimate. Fuel cells would be a more of a competitor, I think, than a conventional battery per se.
So you built an electric...
Fuel, right?
Yes. So you built an electrochemical Carnot engine is what you've done, I take it.
Right.
Is there anything wrong with building just a mechanical Carnot engine?
The challenge in building a mechanical Carnot engine is getting the constant temperature expansion and constant temperature compression that you need. The advantage of the membrane is a few microns thick. So as the gas is expanding through it, as long as you keep the substrate that the membrane is on, the electrodes, at a constant temperature, then the gas will expand through at constant temperature. It's a lot easier. In an engine where you have a piston or something like that, or even a turbine as the gas is passing through, especially generally in a turbine, it's going to be going through really fast, so you'd have to transfer the heat in a way that it's heating up as it expands, or it's transfer heat as it expands so the temperature doesn't drop, because normally gas temperature will drop as it expands. So the challenge is in how you get the heat into the gas that in a time fashion that works in a practical sense.
So there might be some nanotechnology device that could be built that could bring the scale of all of those things down?
Possibly. I'm laughing because when you start talking about nano, you're talking about surface area, and if you're talking about gases moving over something that has high surface area, you're talking about a lot of friction, and I mean there are always trade-offs and challenges, and it's an intriguing thought. So.
Thank you.
You mentioned one of your charts showed up there that potential applications included implants. It would have to be nanotechnology for that, right?
No, we actually did an analysis. You know, it turns out that the Carnot efficiency between 37 degrees and 25 degrees is about 3.25%, something like that. So if you're just sitting still, your body generates about 100 watts of heat. And by far the majority of that actually comes from your head. So if you have 100 watts of heat, if you could capture all of it, you could literally generate, in an ideal cycle, about 4 watts of power. That's a very significant amount of power. Clearly, in a real-world practical situation, you're not going to do that, be able to achieve that, but you could achieve enough to power a neurostimulator or a pacemaker, something that took a small amount of power. So that's what that was based on.
Did you try multiple layers of metal oxides and put some? Did you try metal oxides multiple layers and put none of that, like ultracapacitor or supercapacitor? Maybe you can increase the flow to electrons. By this way, for example, from hot side to cold side, electron flow and conductivity increases, efficiency may be increased.
There's a candidate. We've been talking about collaborating with the university, and we're literally interested in ways that we could work together. If I'm understanding you, you're talking about this system, or you're talking about
Your system, yeah, JTA.
Okay, you're not talking about thermoelectrics, because people have worked on superlattice structures where they tried to make thermoelectric devices, which is semiconductors.
Seebeck effect.
Right, Seebeck effect, and they tried to make multi-layers in the structure and make each layer thin enough that it's on the order of the wavelength of the heat wave, if you will, and as a way of setting up a resonance so you don't have the heat transfer. And they have not had very much success at that. And even then, I think their most ambitious goal was to try to achieve about 20% efficiency. The challenge that they have in trying to do that is that because you're talking about nano layers, when you start trying to go to some appreciable operating temperature, you set up diffusion because you know how things, you get more molecular or atomic mobility as you go up in temperature. So if you're talking about ceramics, you're talking about literally having those layers diffuse into each other, so you lose the effect. I didn't say a lot about applications for the technology, but there's one efficiency curve where we've actually done analysis that suggests that something upwards of 80% of Carnot, because in the real world you're going to have friction, but getting to those kind of performance levels and operating on heat sources in the 1,000 degrees centigrade range, you can actually get it up into the 60% conversion efficiency levels. That would be a remarkable breakthrough in applications like solar energy conversion and so forth. There's no way that anybody's even conceptualized how one would get Thermoelectrics to operate at those efficiency levels.
Yes, it's more of a non-technical question, but what type of skills did you develop early on in your life that caused you to attain these great heights? Did it start when you were, like, say, 10 or was it 18? You had to be in college? And what advice would you give to, say, some of the young people here on how to,
You mean
skills to reach those heights?
You mean besides being stubborn? Not knowing any better than to try something that, it's funny you ask that because I was just at Hasbro earlier this week and kind of lamenting about the fact that there are people in the toy industry who've literally spent their entire careers in that industry and have tried to come up with innovative toys and who have not experienced the success at a level that Super Soaker or had the kind of impact that a Super Soaker has had. And I kind of parachuted in from the space industry, or space program, because I was working for NASA before, even at the time that I came up with the idea for the water gun. I'm certainly not a battery expert. Well, I guess I am now. But I didn't start out as one. I'm a mechanical engineer. I took a lot of electronics courses when I was in school because I wanted to know as much as I could. But I really don't have an explanation other than just stubborn and not knowing any better than to tackle problems that other people who would have known better than to tackle. Okay.
A couple more questions in the back and probably one in the back.
How safe is this system that uses hydrogen?
Fairly safe, actually. It doesn't require a large volume of hydrogen, and the hydrogen is not consumed; it just circulates inside of it. So, reasonably safe. Hydrogen is very difficult to contain, as you probably know, because the molecule is extremely small. It turns out that oxygen-free copper, or copper, pure copper, is a good containment material for hydrogen, whereas hydrogen will tend to form a hydride with most other metals, which cause them to become brittle, which causes them to crack very easily. So it turns out that was one of those situations where Mother Nature chose to cooperate with us, because in a lot of situations we're fighting Mother Nature, but copper is a good heat transfer material, so we can get heat in and out very easily because it's very conductive and it's also stable with the hydrogen. It's a challenge on the high temperature end because if you're talking about going up to 600 to 1,000 degrees centigrade for the high temperature part of the engine in non-medical applications, then you got to have ceramics or some other materials that are stable and that can contain the hydrogen. But those are all, again, engineering challenges that I would love to collaborate with the university on.
I'd like to ask about the possibility of a nickel-cadmium metal, which does not have any problem for recycling, recharging. On the other hand, lithium-ion has that problem. That's what the dream diagram is showing the problem. For the long-term longevity of durability. What do you think about NICAD's potential with respect to lithium ion?
Well, you know, in reality, it comes down to performance. The NICADs can't contain the amount of energy for a given size battery or for a given weight battery that the lithium ion can. And if, you know, if you're aware, you know, in an aircraft application or in most applications, you know, size and weight are very critical. This is why the entire electronics industry has gone to lithium ion and abandon NICADs, if you will, because you get a lot more energy per unit volume and per unit weight. I think cadmium itself has actually been banned in some countries, particularly in Europe, because it's a toxic material. So for various reasons. But most of them, I think, by and large, are performance related.
Another thing that you talked about ceramic battery, are you referring to SOFC, solid oxide fuel cell, like LSP, lanthanum, strontium, cobalt, manganese?
For the,
Is that what you are talking about?
when I said ceramic,
Right.
the,
But that requires a high temperature synthesis.
that's right. For which application?
Well, it is for fuel cell.
The reason, for the fuel cell, for the JTEC, for the engine, when I said ceramic, yes. Strontium dope zirconate, for example, is a good proton conductor. It's a pure proton conductor at high temperature. YSZ, on the other hand, is a oxygen ion conductor, and we've actually done one of the SBIRs that we've just finished with Georgia Tech again. It was a different project altogether. We had an SBIR to look at use of the JTEC to generate power on a scramjet type aircraft, or off of a scramjet engine. Because the scramjet does not have a rotating shaft, the problem is you don't have a shaft to turn the generator as you would on a conventional aircraft. But you do have the scramjet that produces a lot of heat. So the idea was to use the heat from the scramjet to produce power. In that application, we actually did look at oxygen ion conductors, yttrium-doped strontium zirconate, for example, as an oxygen ion conductor, because we were at high temperature, and we could actually have the low temperature end of the JTEC would actually be high temperature also. So we were bringing the heat in at about 1,000 degrees, and in the models we were rejecting heat at about 600 degrees. In that kind of situation, you could actually use an oxygen ion conductor. But for the JTEC, the basic system, the idea is to have a proton conductor, because you can't get an oxygen ion conductor that works very well at low temperature. And when I say low temperature, I'm talking about below 200 degrees C, around 100 degrees. 150 degrees is where we'd like to have the low temperature end of the engine work, because you still need a temperature difference in order to reject heat to the environment. Okay?
You may have noticed that late 80s to mid 90s, almost a decade or so, the fuel oxide, solid oxide fuel cells rose as a research subject. But for the last 15 years, it's almost like it's dead. What do you think about the possibility of using this technology? Is there any chance at all?
That solid oxide fuel cells will have a future? Is that what you're asking? I'm trying to understand. I'm sorry, I apologize, but
I'm talking about this place is declining.
We will have time after today. We set aside some social and question time. So if some of the questions you had has not been answered, if you have the opportunity and inclination, you want
that's fine. I'm enjoying this. Just the answer to that question. If you've heard of Bloom, I'm sorry. Bloom Energy has a solid oxide fuel cell that it's actually commercializing.